Numerical systems can be seen in many forms around us every day. The 24-hour clock and the 12-hour clock are two simple examples of two different systems that ultimately represent the same information. When a 24-hour clock reads 20:30, a 12-hour clock will read 8:30 p.m. Again, this is the exact same information. We're just displaying it in two unique ways. This idea is the heart and soul of how different number systems work. Let's take another quick look at a joke t-shirt. It reads, "There are 10 types of people in the world, those who understand binary and those who don't." The joke here is that 10 or 10 in the binary number system represents 2 in the system that we're all familiar with called the decimal number system. In this lesson, we will take a look at the binary number system and the decimal number system. Specifically, we will look in detail at how they work, how to translate between them, and why we use them. The most common number system in the world is by far the decimal number system. This is what we all learned when we first studied math at primary school, or even before that, when we were babies and simply learned to count. The decimal number system has 10 numbers, 0, 1, 2, 3, all the way up to 9. And we call this type of system a base 10 number system. And since humans have 10 fingers, it makes perfect sense that we would prefer counting to 10. However, where the decimal number system consists of 10 numbers, 0 to 9, the binary number system consists of only 2 numbers, 0 and 1. So we call this a base 2 number system. For a quick example, the two numbers on the screen represent the same value, 22. But each number is displayed in a different number system, decimal, represented by the subscript 10 in parentheses, and binary, represented by the subscript 2 in parentheses. Let's take a more in-depth look at each of these number systems and figure out how to translate between them. Let's take a simple number, like 7. To translate it to binary, we divide it by 2, which equals 3 remainder 1. Now, we bring the 3 down and divide 3 by 2, which equals 1 remainder 1. Now, we bring the 1 down and divide 1 by 2, which equals 0 remainder 1. Now we take all of the remainder values and put them down here. And the binary value of 7 is 111. Then we add a subscript of 2 in parentheses to represent that we are using a binary number. It really is as simple as that. For another example, we'll take a larger number, 77, and convert it to binary. To do that, we'll use the same process as before. 77 divided by 2 equals 38 remainder 1. Bring the 38 down. 38 divided by 2 equals 19 remainder 0. Bring the 19 down. 19 divided by 2 equals 9 remainder 1. Bring the 9 down. 9 divided by 2 equals 4 remainder 1. Bring the 4 down. 4 divided by 2 equals 2 remainder 0. Bring the 2 down. 2 divided by 2 equals 1 remainder 0. Bring the 1 down, and 1 divided by 2 equals 0 remainder 1. Now we put all of the remainders next to each other over here, and we find that the binary representation of 77 is 1001101. Just as important as converting from decimal to binary, we must learn how to convert from binary to decimal. Luckily, this process is somewhat easier. For an example, let's convert 1001101 into decimal. To do that, we build the following formula. To build this formula, we found how many different places the binary value has. In this case, it has 7 places. Then we spread out the binary number and multiply each number by 2 to the exponent of its place, all in order. The calculation might take a moment, but it will come out to 64 plus 8 plus 4 plus 1, which is 77. Now that we've learned the basics of how to convert back and forth between decimal and binary, let's take a look at how decimal addition and subtraction looks. Since binary is a number system just like our decimal number system, almost all of the rules you learned in primary school math still apply. If we have two decimal numbers, 1001 and 0011, we can put them in the same addition format and add them together. 1 plus 1 equals 0, carry the 1. 1 plus 1 equals 0, carry the 1. 1 plus 0 equals 1. And 1 plus 0 equals 1. So the answer is 1100, which, if we convert everything over to decimal and perform the addition, 9 plus 3 is indeed 12. Feel free to convert the 4-place binary number 1100 to decimal to double-check our math. Let's go the opposite way and see an example of subtraction in binary. We'll use 1001 minus 0011. Again, we can put them in the same format that we're used to and then subtract. 1 minus 1 is 0. 0 minus 1 means we have to borrow. So this turns the 1 into a 0. We borrow again. So 2 turns into 1. So now we have 2 minus 1 equals 1. And 1 minus 0 equals 1. So our answer is 0110. And if we convert these numbers over to decimal, we can see that 9 minus 3 equals 6. And again, you can convert the binary answer to decimal to double check it's the correct answer. These examples show you how the binary number system applies the same rules as the decimal number system, but that everything is simplified by only having zeros or ones. Multiplication and division and even long division can be done as well. However, we'll skip those for now. In digital electronics, it is common to use LEDs as a way to output information to designers to let them know if there's a problem. Since LEDs can only be on or off, they make for perfect binary number displays. If you take these 4 LEDs, for example, and convert their state into binary, 1 equals on, 0 equals off, we would get 1001. Converting that further into decimal, we get 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0, which in decimal equals 8 plus 0 plus 0 plus 1, which equals 9. One other idea that we just zoomed through without realizing it is something called binary coded decimal, or BCD for short. BCD is the translated value of a binary number into the decimal number system. Each decimal number, 0 to 9, has a correlating 4-digit binary number, as you can see in the chart. And at the very bottom, you can see the 1001 that we converted before is indeed 9 in the decimal number system. In the real world, we rarely see the binary number system in use. We can make the analogy that a light bulb turned on or off can represent a binary 0 or 1, but we're not really using the binary number system in that case. The most common place to see the binary number system in use in the real world is on simple binary clocks or watches like these. On the flip side, inside of the computer engineering world, binary is used everywhere. A quick and simple example are how letters, numbers, and symbols are encoded for transport through the internet. A system called ASCII, short for American Standard Code for Information Interchange, can encode the entire English alphabet, numbers, letters, and symbols into 128 unique numbers. You can see which letters and numbers correlate to which binary, decimal, and hexadecimal values in the ASCII chart on the screen.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Next time, we'll learn about logic gates and get a feeling for how they work, what's inside of them, and how we use them with digital electronics.